What's up? My name is Matthew, and in this video we're going to talk about the graphs of some other trig functions. In particular, we're going to look at tangent, cotangent, secant, and cosecant. Let's go have a look. The first thing we need to talk about is the actual tangent functions, and we need some values that we can that will allow us to plot some points, and then we'll do some graphing, and then we can worry about cotan. So let's see about generating some values here. Now remember that the period of the tangent function is pi. Sine and cosine have a period of 2 pi, but tangent and its reciprocal function cotan have a period of pi. And in this table, there's this bracket that you're seeing up here, and what's being illustrated is that the distance, literally when we're graphing horizontally, the distance from negative pi over 2 to pi over 2 is pi. So that's the period of the tangent, function that we're going to look at. In sine and cosine, when we looked at those graphs, at least in my videos, I usually examine those going from 0 to 2 pi. So it's interesting that we're moving to the left of the y-axis in this case. But so it is. If we plug negative pi over 2 into the tangent function, we get a value of undefined. And there are a couple of ways to explain that. One is that's just what it is. Another way to explain it is that I will remind you that the tangent function is equal to sine of the angle measure divided by cosine of the angle measure, and cosine is equal to 0 at negative pi over 2. Therefore, you've got division by 0, so the tangent function ends up being undefined. At negative pi over 4, we have a y value of negative 1, and then up to 0, and then to positive 1, and then undefined again, because cosine of pi over 2 is equal to 0, division by 0, undefined. And then, because of the pi periodic nature of the tangent function, our y values start repeating. So then we would have a negative 1 again, and then 0, and then 1, and then undefined. All right, so as x gets closer and closer to positive pi over 2, tangent, or sine over cosine, the y values start moving toward positive infinity. So again, that's as our x values are getting really close to pi over 2 from the left. We're going to look at it graphically in a second. As our x values move from right to left out of the origin, our curve, our tangent graph, is going to dive down, and our y values are going to start moving in the direction very rapidly of negative infinity. Let's see what that looks like. I'm going to say that, let's see. So the existing y-axis that you're seeing here, let's go ahead and use that. And then down at the bottom here, let's label and say that this is negative pi over 4, and 2 more boxes to the left is going to be negative pi over 2. The y-axis is obviously 0. To the right 2 boxes is going to be positive pi over 4, and 2 more boxes to the right is pi over 2. And then vertically, so above and below the horizontal axis here, let's go up 2 boxes for positive 1, down 2 boxes for negative 1. And then we'll plot some points, which is kind of interesting because the very first thing that we're going to plot is not a point at all. We're going to plot an asymptote. So at negative pi over 2, because the tangent function is undefined, I'm going to draw this vertical dashed line at negative pi over 2. And then I'm going to do the same thing at positive pi over 2. Let's just get those asymptotes out of the way. So those are resulting from the fact that our tangent function is undefined at negative and positive pi over 2. Also, those vertical asymptotes are the result, the graphical result, of division by 0. which you may or may not recall or be familiar with. When you were working with polynomials and rational functions, if there was an x value that caused division by 0, then the graph had a vertical asymptote at that x value. Unless it was a removable discontinuity, then it showed up as a whole. But we won't get into all of that again. Next, let's plot our 3 actual points. So at negative pi over 4, we're plotting negative 1. At 0, we're plotting 0. At pi over 4, we're plotting a y value of positive 1. And then we're going to sketch this curve into here. And I'm going to draw it from the bottom left. Have a look at this. Because that's an asymptote, I'm going to start my graph out very close to it, and then come up and bounce through these 3 points. And this graph looks a little bit like a propeller, and it takes a little practice. It's taken me some practice anyway to be able to draw this so that it looks pretty close to how it's supposed to look. This graph looks a lot like the graph of x cubed, except it's confined between these vertical asymptotes. Yeah, okay, and then let's keep moving to the right. So I'm going to go back down to the bottom of my graph. I've got pi over 2. I'm going to move to the right 2 boxes. That's going to be 3 pi over 4. To the right another 2 boxes is going to be 4 pi over 4, 2 pi over 2. Maybe we should just call it pi. Let's call it pi. And then let's keep going. Let's go to 5 pi over 4. And then 6 pi over 4 is 3 pi over 2. That can't be right. That is right. 3 pi over 2. 1 pi over 2. 2 pi over 2. 3 pi over 2. Okay, I'm just counting my way along. I just did this. 1 pi over 2. 2 pi over 2. 3 pi over 2. Just to make sure that I'm labeling my horizontal axis correctly. Because of the periodic nature of the tangent function and the distance between those vertical asymptotes is pi, I have my first asymptote here, and then I move to the right pi, and I put another asymptote, and now I'm going to move to the right another distance of pi and put in another asymptote. Now that's not on the table that we were just working with that's just above this graph, but I'm going to put it on there anyway just to be a little more thorough. Let's plot some points. Check this out. At 3 pi over 4, we're at negative 1. At pi, we're at 0. At 5 pi over 4, we're at positive 1. And then at 3 pi over 2, we're doing the vertical asymptote again. Get that in there somewhat nicely. And then you can draw yourself another iteration of the curve. See if you're getting any better at this. It's such a subtle movement, and I'm zoomed in, so I'm drawing this graph the size of like the largest iPad that they make. So I'm having to move my hand and then keep drawing my curve. Anyway, for the most part, when we talk about the graph of this function, we're going to stay between negative pi over 2 and pi over 2. But obviously, a full rotation is 4 pi over 2, or 2 pi. And I haven't even, in this graph, made it up to 2 pi. However, 0 and 2 pi are kind of equivalent. They're coterminal angles. And the total width of this graph that we've drawn now is a total distance of 2 pi, so I bet we could make it work. And we will. We'll have to make it work. We'll come back and talk about coterminal angles some more as we go along. All right, the graph of cotangent. So the period of the cotangent function is pi. And the distance from 0 to pi is pi. So interesting, we're not going from negative pi over 2 to pi over 2. In this table, we're going from 0 to pi. And not only is the period of the cotangent function equal to pi, but remember that cotangent is literally the reciprocal of the tangent function. And I'm going to pop back up to this graph real quick. The x values that we're going to plug into this table down below, we're going to plug in 0. What are we plugging in? Is it 0 and then to pi over 4? Okay. 0, pi over 4, pi over 2, 3 pi over 4, and pi. That's what we're going to do in the table below. The x values that I just highlighted, not changing. We're using those again. So what's going to change? The answer is the y values. And what's the relationship between the y values that we're seeing present on this graph compared to the y values that we're going to see on the graph of the cotangent function? Those y values are going to be the reciprocal of these y values. So let's just talk about what they're going to be before we go write them in. Look at this y value right here. What's that y value? 0. What's the reciprocal of 0? 1 over 0. 1 over 0, that's 1 divided by 0. Division by 0, that's undefined. Graphically, that should show up as an asymptote. And it will when we get down to graphing the cotangent function. And then here's our next y value. That's a y value of 1. The reciprocal of 1 is 1 over 1, which is 1. That'll be our y value. And then there's this y value, which is undefined. It's actually, well, from the left, it looks like positive infinity. From the right, it looks like negative infinity. Either way, it's a really big number. And what's the reciprocal of a really big number? Something darn close to 0. So remember, division by 0 gave us undefined. The reciprocal of undefined is going to give us the 0 back. So we're going to plot a 0 at pi over 2. The reciprocal of negative 1 is negative 1, and the reciprocal of 0 is going to be 1 over 0, which is going to be undefined again. So we're going to have asymptote, positive 1, 0, negative 1, asymptote. Let's get to it. We'll keep using blue. All right. Starting from the x value of 0, we're starting with an asymptote, undefined. And then we're going to negative 1. Is it negative 1 next? No, it's positive 1 next, sorry. Positive 1, and then 0, and then negative 1, and then undefined. 1, 0, negative 1. 1, 0, negative 1. Okay, just making sure. And then, because of the periodic nature of pi, our y values start repeating, so we would go to a positive 1 next, and then to a 0, sorry, there we go. And then to a negative 1, and then to undefined. All right, as x approaches 0, cosine over sine this time is approaching. Let's graph it first, and then talk about what those are approaching. All right, so the points that we're plotting this time, at 0, we have, well, let's see. How did we do this? I think we were using blue down here. Let's put 0, pi over 4, pi over 2, 3 pi over 4, and pi, so 2 boxes at a time. Vertically, we'll still use 2 boxes up as positive 1, 2 boxes down as negative 1. And then we'll plot some points. The first point that we're plotting, strange, is an asymptote, and it's right on the vertical axis. So I'm putting it just next to it so that I can still see it. And then 2 boxes to the right, we are at positive 1. 2 boxes to the right, we go to 0. 2 boxes to the right, we go to negative 1. 2 boxes to the right, at a y value of pi, we have another vertical asymptote. So between these two asymptotes, you see that the curve rises to the left and falls to the right. Rises to the left and falls to the right. That's the opposite of what the tangent graph did between its first 2 asymptotes. It was falling to the left and rising to the right. So just some comparisons between the two. Oh, would you like to come in? Okay. Whatever Sophie wants, Sophie gets. And then let's graph one more iteration of this, just for your reference. 2 boxes to the right, we'll go up to 1, 2 boxes to the right, to 0, 2 to the right, down to -1, 2 to the right, another asymptote. And rises to the left, falls to the right. I met with a student today who said, I really appreciate your videos. They're very detailed, they're very informative, but you're absolutely right. I have to watch them at least 1.5 speed. And I agreed. I said, for sure, when I watch my own videos, I watch them at least 1.5 speed. Because it's slow going. I'm a very detailed person, and I want to make sure we get everything right the first time. But that causes me to be a little long-winded sometimes, and the videos get a little lengthy. You can probably write faster than I can. I have to be very careful about the way that I write because my handwriting is not great, to be honest, in case you didn't notice. So I try to be kind of cautious and make sure, especially writing with this goofy pen, I want to make sure that it's legible. All right, so there's your cotangent graph. Let's go back up and answer these 2 questions real quick. As x approaches 0, in this case from the right, and let me just leave this right here, and if you look down at the graph, notice the green highlighters climbing up there, hopefully you can see that. As our x values are approaching 0, so we're moving in on that vertical asymptote from the right, our curve is going up toward positive infinity. And as that graph approaches pi, so as my green highlighter starts moving to the right, so that my x value is closer to pi, those y values start diving down toward negative infinity. So you could put a negative infinity in here. All right, that's tangent. X values stayed the same. We plotted reciprocal y values. X values stayed the same, plotted reciprocal y values. All right, let's quickly fill in this table. What's the period of the tangent function? And then you say pi. How about the period of the cotangent function? Same, pi. And now you've got an image in your mind that you just drew meticulously, which will hopefully be able to jog your memory, and you can see that period of pi between those asymptotes. The domain of the tangent function. Okay, so this gets a little bit tricky. In the tangent function, because we had those asymptotes, which is where division by 0 was occurring, our function is undefined there. We even wrote undefined. So we have to describe our domain in such a way that we leave out those problematic x values. And one way that you can describe them is like this. Using set builder notation, I don't like that bracket. Let me zoom in. Using set builder notation, the domain is the set of all x values such that x does not equal negative pi over 2. That's where one of our vertical asymptotes was, plus k, or sometimes the variable n is used, times pi. And k is a member of the set of integers. How's that for fancy? So again, it's the set of x values such that x does not equal negative pi over 2 plus k pi, where k is an integer. Integers, let me remind you, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. You might think of them as whole numbers, but technically they're not whole numbers because they include the negatives. So what that really says is negative pi over 2 plus negative 3 pi's, plus negative 2 pi's, plus negative 1,000 pi's, plus 11 pi's, or 17 pi's. Either way, we're moving forward or backward, to the left or to the right, multiples of the period of the function. We're hopping from asymptote to asymptote in both directions and leaving out those x values from the domain. Something similar for the cotangent function. The domain, we have to leave out different asymptotes, different x values. This time it's the set of x values such that x is not allowed to equal integer multiples of pi. Again, where k is an integer. So these are legitimate symbols. This one right here looks kind of like a lowercase c with a little bar in the middle of it. And actually I drew this pretty accurately. As I recall, it's called a blackboard z, and it represents the set of integers, all of the integers. It's a z because z is the first letter in the German word for numbers, I believe. I don't know if it's specifically integers, but I believe the word is Zahlen. Z-A-H-L-E-N, something like that. What about the range of the tangent function? And the cotangent function for that matter. Look at these red curves. Those things go all the way up and all the way down, and there's no break. Vertically, there's no break. So we're going from negative to positive infinity on both the tangent and the cotangent as far as range is concerned. So let's use interval notation there. Negative infinity, positive infinity, and ditto over here. For the tangent function, the vertical asymptotes occurred at those problematic x values. So vertical asymptotes, I suppose we could list this as x equals negative pi over 2 plus k pi, or n pi. And for cotangent, very similar. This is just x equals k pi. If you'd like to put k as a member of the set of integers next to both of those, you may. I'm just sort of carrying this down with us. The x-intercepts. All right, let's go back and look at the tangent graph. Where do the x-intercepts happen? Going way back. All right, x-intercepts are happening at 0 and at pi. And because of the periodic nature of the tangent function, you can bet that the next one would occur at 2 pi and 3 pi as we keep going off to the right. If we went off to the left, we would have x-intercepts at negative 1 pi, negative 2 pi, negative 3 pi, and so on. Incidentally, these are the points that when we took the reciprocal, in order to graph the cotangent function, it's those points that gave us the other asymptotes. So anywhere there's a 0 on the tangent graph is where we have an asymptote on the cotangent graph, and vice versa. Maybe we can use that to our advantage so we don't have to be scanning up and down between these pages so frequently. I can only scroll up and down so many times before I'm going to start to get nauseous, I think. So the x-intercepts we just said are happening at x equals k pi. Negative 3 pi, negative 2 pi, negative 1 pi, 0, the origin. We saw that as our first one. And then over to the pi. That was where we saw our second x-intercept in that tangent graph. And look at this. The x-intercepts correspond to the... Oh, even better. Correspond to the location of the vertical asymptotes for the cotangent function. And the x-intercepts on the tangent cotangent function that's a 2 down there, by the way. Those intercepts are happening where the tangent graph has It's x-intercepts. I said that backwards. The x-intercepts for the cotangent graph happen where the tangent graph has its vertical asymptotes. So if you want to put in some sort of a note saying that, you know, somehow indicating to you that these correspond, that should help sort of stitch the picture together for you a little bit better. Both of these functions are odd functions. And now we start shifting them around. We're going to start modifying them. And we did this in the conversation that we had about the sine and cosine graphs. Except there we used a word which we won't use here. We used the word... Have you seen the word that I'm looking for? I'm looking for the word amplitude. That's it. Amplitude was how far vertically we were stretching those graphs. With the tangent function and cotangent function, because they go all the way up to positive infinity and all the way down to negative infinity, to call it a stretch or a modification in amplitude or height doesn't really make sense because they're infinitely tall, both of them. There is still the opportunity to vertically stretch these graphs. We're just not going to call it amplitude. What we are going to have is Sophie walking on the iPad, of course, in typical form. We are going to have asymptotes that will get modified as a result of horizontally stretching or shrinking the graph of the tangent function. And we'll talk about those. These are formulas that describe sort of how that's going to happen. That's fine. I take a little bit more of a commonsensical approach at those, but that's fine. We can use those. X-intercepts are halfway between each set of asymptotes. Thanks for that, right? We could picture that. And then there are these points in number 3, they're calling these kind of quarter points, that 1/4 and 3/4 of the way through the period. And as we saw, they were occurring at positive and -1 vertically. Those were y coordinates. When you bring in these a values up here in these two equations, those are causing the vertical stretches or a shrink, and those are going to impact y coordinates. And the y coordinates that we've worked with so far for these two graphs are -1, 0, and +1. Well, if you multiply by 0, nothing happens. But if you take that a value that I just circled and you multiply that into those y coordinates, those couple of points are going to change. All right, so we'll see that happen. And we definitely want to graph at least one full period of these functions. So let's see what we can do. Is there, so we, like I said, we're not going to use the word amplitude, but is there some kind of a vertical stretch? So that's what I'm going to call it. Vertical stretch or shrink. If you want to put a little note in there that says that was previously called amplitude, or just in quotes you could write amplitude. It's not the worst idea. So you have some consistency between what we're looking at, between all these graphs. And here, we do have that modifier. That's our a value, which here is equal to 1/2. And in order to have that impact our graph, we're going to take our y values and we're going to multiply them all by 1/2. And then inside of our tangent function, we have our b value that we're considering next. And that's what's going to cause the horizontal stretch or shrink. Horizontal, oops, I move my hand and sometimes the screen just kind of flies around. Those are quotation marks, stretch or shrink, horizontal stretch or shrink. Our b value here is equal to 2. And so the new period will equal the original period divided by our b value. And what was the original period of the tangent function? Pi. For sine and cosine, we were putting a 2 pi right here, but with the tangent and cotangent functions, we have to put a pi there. We're dividing by this b value of 2, and our new period is pi over 2. So it's been compressed. from the left and from the right. How do we enact that? We're going to have to take our x values and multiply them by 1/2. Now in this problem, look at the original equation, there is no c value. There's no vertical shift. There's no horizontal shift. There's no phase shift. Nor is there a d value. So there's no vertical shift either. So this one is a bit of a starter function for us, which is fine. Now when we're graphing the tangent function, the very first time we looked at it, we looked at some certain x values. We started with our horizontal, ooh, you know what? There was a nice way to do this. How did I do that before? Is it here, and then I can draw a line? Yeah. Because we want to be able to put our original x values and our new x values, similarly for our y values. Okay, get rid of that line tool, and original, and that's come out very good. Original and new. For y values, we'll have original and new. And the original x values that we worked with when we first graphed the tangent function, we plotted a vertical asymptote at -π/2, and then we plotted a point at -π/4, and then at 0, and then at π/4, and then a vertical asymptote at +π/2. The new x values that we're going to work with, as we wrote down right here, are going to be half of what those old x values were. So let's put in, I'm going to switch colors, -π/2 times 1/2 makes -π/4. And then -π/8 is half of a π/4. And this is still 0, +π/8, and then multiply that +π/2 times 1/2, and we get +π/4. So those are the new x coordinates that we're going to plot. And our original y values were undefined. That was our vertical asymptote at -π/2, and then we went to -1, and then to 0, and then +1, and then our right-hand vertical asymptote for that first period. Now, what are we doing to our y values here? Interestingly, coincidentally, I might add, we are halving them. We're multiplying them by 1/2. So I'm switching colors back to red for my new y values. Infinity times 1/2 is still infinity, so we've still got an asymptote that we're working with. That's a highlighter. There we go. Still undefined, still an asymptote. This is going to be -1/2. Half of 0 is still 0. This is +1/2. And undefined times 1/2 is still undefined. Nice. So let's plot some points, or asymptotes. At -π/4, we have an asymptote. I'm going to put tote. And then here we've got -π/8, -1/2. And then we've got 0, 0, and +π/8, +1/2, and at +π/4 we have another tote, another asymptote. Let's use the same, I'll leave that on the screen for you. Let's use the same scale as we did on the previous graph. So all the way to the left is going to be -π/2. And then -π/4, but one box to the left of our vertical asymptote, let's also this time include -π/8. We're going to need it. 0 is the y-axis, then +π/8, and then one more box to the right for +π/4, then two boxes to the right for +π/2. On the vertical axis, off to the left there, let's still use +1 is up 2 boxes, -1 will be down 2 boxes. There you go. And let's switch colors and draw some stuff. At negative pi over 4, we've got a vertical asymptote. Previously it was at negative pi over 2. Now we've squeezed it in. It's at negative pi over 4. Let's do the other one while we're at it. At positive pi over 4. Excuse me. I could edit that out, but I'm just trying to keep it real. At negative pi over 8, we are now at negative 1/2, still at 0, 0. Then to the right at pi over 8, we're up at 1/2. And we can draw our compressed version of the tangent curve. So we're still diving down to the left. That thing's tracking along the asymptote for longer this time. Previously it curved, at negative 1, but now it's curving not until we get closer to negative 1/2. And then through the origin and start curving. Hug that vertical asymptote. Don't cross it. Don't even touch it. I liked the original tangent graph better. It was wider. It was a bit curvier. This is it. We've graphed one period of our new or transformed tangent function. You could copy and paste this thing to the right as many times as you want, or to the left, although you'd go off the page. But the periodic nature of the tangent function says we can do that. All right, nice job. That is the graph or a graph of a transformed tangent function. Cotangent works the same way. If you're one of my students, let's do one of these in class. I can tell you that there's going to be sort of a vertical stretch. You're going to have to multiply your y values by 3 because of the a value. The b value is 1, so there's no horizontal stretch or shrink. But you do have a c value. A, b, so a equals 3, b equals 1. And what's your c value? Careful. Your c value is negative pi over 4. Remember, this really says x minus negative pi over 4. The minus negative, it's hiding right here. It looks like a plus sign, but that's not a plus sign. It's a minus negative. All right, so vertical stretch of 3, horizontal shift or phase shift to the left, pi over 4. To the left, that left, your left. And that's it. This one's just a stretch and a horizontal shift. So you're going to have vertical asymptotes at negative pi over 4 and positive 3 pi over 4. See if you can do a little bit of preliminary work on that. If you're one of my students and you want to give that sort of attempt that one, that would be great, and you can bring that to class with you. We'll look at it together. I want to keep moving because we're already 38 minutes in. Although if you're watching at double speed, it's only 19 minutes. That's nice. Remember that cosecant is the reciprocal of the sine function, so this is 1 over sine x. Everywhere sine of x has a 0, cosecant is going to have a, what's the reciprocal of 0? 1 over 0, which is division by 0, which graphically is going to show up as a vertical asymptote. Vert tote. Everywhere everywhere sine of x equals 1, cosecant of x will still equal 1 because the reciprocal of 1 is 1. Everywhere the sine of x is equal to negative 1, cosecant of x is equal to negative 1. I think you know why. In the right-hand column, secant is the reciprocal of the cosine function, so I've got 1 over cosine x there. Everywhere cosine of x has a 0, secant has a vertical asymptote. Asymptote. A-S-Y-M-P-T-O-T-E. Asymptote. Some. And then the P is kind of silent, and then it's tote. T-O-T-E. Not taupe, like the color, but tote, like the bag. All right, it's getting weird again. Everywhere cosine is equal to 1, secant's equal to 1 everywhere. Cosine of x is equal to -1, secant's equal to -1. There we go, okay. Oh, I'm so glad we didn't have to graph that ourselves. Look at this thing. Let's look at some highlights of what's going on here. The period, because we're working with the reciprocal of the sine and the cosine functions, well, here we're looking at the graph of cosecant, so it's the reciprocal of the sine function. The period is equal to 2 pi. Now, the domain is different. There's a domain issue because those blue curves that you're looking at are sandwiched between asymptotes. And those asymptotes are x values that we need to leave out of the domain. So the domain is all real numbers except integral or integer multiples of pi. -1 pi, 0 pi, +1 pi, +2 pi, and so on. The range, look at those blue curves. This one does have or contain a point that has a y value of +1, but otherwise all the rest of the y values are above +1. And this downward facing curve does reach a point that has a y value of -1, but otherwise all the rest of those y values are lower. So we're leaving out all of the y values between negative and +1. So check out how they wrote the range here. The range does contain the negative and +1. Vertical asymptotes are happening at integer multiples of pi, and cosecant is, I've never seen this before. Cosecant is an odd function because it has origin symmetry. Secant, however, is an even function. I'm going to leave a note in the comments because I just realized, and I'm embarrassed, I've been teaching this for a little while now. I have previously said in a previous video, at least once, specifically when we were talking about even and odd functions, I said that secant and cosecant were both even functions. That's not true. The cosecant function is an odd function because it's symmetric about the origin, and because it's an odd function, the secant of -x is equal to the cosecant of -x is equal to negative cosecant x, which is typical for an odd function, okay? If you're one of my students and you've got your notes, or even if you're not one of my students, you got your notes and you wrote down the note about an odd function, even and odd functions, pause this video right now. I'll still put the note in the comments, but pause this video right now. Go back into your notes, find that and fix it, please. And make sure that you're listing cosecant as being an odd function. Sorry about that. Maybe I could even find it. Let's see. I found it. It's in the 4.2 notes on page 6 of 12. We need to make sure that we take cosecant. Even functions were cosine and secant, and I listed all the rest of them as odd functions. Sine is an odd function. Maybe I didn't make a mistake. Cosine and its reciprocal function are secant. Oh. Thank heavens. I really thought I had messed this up literally for years. But I did not. Okay, so we're good. We don't have to change any of our notes. Cosecant is, I don't have my highlighter on, but cosecant, we did list that as being an odd function. Secant's listed as being an even function. Great. Okay, so the primary function and its reciprocal function, cosine and secant, those are the only two even functions. Everything else is odd. Crisis averted. And right where we left off, I can take away... Will I still be able to erase these things? Oh, good. I don't need to see that. Give me a real panic attack. Okay, so there's your graph of the cosecant function. Here's your graph of the secant function. You've got asymptotes. You should examine this in some detail, okay? These are, what you're seeing here though is, and above this one are the basic graphs of cosecant, and then this one is secant. These have not been modified, stretched, transformed, shifted, or anything. The dashed curve that you're seeing in this graph is the original graph of the sine function. And then let's actually do this exercise. I'm going to put a red dot right here, and that's a point on the graph of the sine function, 0, 1. Keep the x value the same and take the reciprocal of the y value. What's the reciprocal of 1? Still 1. Great. So I'm going to use my blue pen and I'm going to plot a point still at 0, 1. Same x value, reciprocal y value. Just so happens the reciprocal y value is still 1. Now let's move to the right a little bit. Let's come to maybe here. I'm not even going to talk about the x coordinate of that point, but this point does have an x value. What is that x value? That's the cosine curve. Cosine. That's pi over 3 is that x coordinate right there. At pi over 3, cosine is equal to 1/2. Adjacent over hypotenuse. Yep, okay. So the y value at that point is 1/2. What's the reciprocal of that y value? What's the reciprocal of 1/2? The answer is 2. So we'll keep the x coordinate the same, but we'll come up and we'll plot a point with the same x coordinate, but a reciprocal y value. So you can see, especially with that example, and let's do one more actually, on the dashed curve, which is the cosine graph, what's the y coordinate at this point? 0. What's the reciprocal of 0? Undefined. And so we have our vertical asymptote at pi over 2. So you can really start to see how the graphs of the reciprocal functions are generated by keeping the x coordinates of the original functions the same and simply plotting reciprocal y values. Again, keep the x coordinates the same and plot reciprocal y values. Use the graph to obtain the graph of the reciprocal. Let's do exactly what I just said. We're going to keep all of the x values the same and we'll plot reciprocal y values. So let's use maybe this point and definitely this point and this point and this one and this one and this one. These points are all so similar. We'll just do all of these. It's only going to take but a moment, and all the way to the left and all the way to the right. Let's do those. At -4, what's the y value? -3. What's the reciprocal of -3? -1/3. And at an x value of -3, we have a y value of 0. The reciprocal of 0 is undefined, so that's going to give us a vertical asymptote. At x equals -2, we're up at +3. Reciprocal is +1/3. And then to the right, x-intercept, reciprocal of the y value. Reciprocal of 0 is undefined, so we get an asymptote. And to -1/3, and to an asymptote. I hate when that happens. Sorry. And +1/3. And the asymptote. Good thing you're watching at double speed. And -1/3. Is that enough information for us to graph whatever the new function is that we need to be graphing? I'd love it to be a little bit more accurate. Let's look at the original blue curve and locate points that have y coordinates of 1. Those are so easy to take the reciprocal of because the reciprocal of 1 is 1. Let me zoom in just a touch. And I would say that my hand is moving things when it's not supposed to. Okay, I think maybe this point right here has a y coordinate of 1, and maybe this point, and moving to the right and down from there, I'm going to -1. here, and then due east from there. There's another point with a y value of -1, and then I'm going up the curve to the point that has a y value of +1, and then due east from there to another point with a y value of +1, and then down the curve to a point that has a y value of -1. There we go. Now, I guess maybe I shouldn't have done those in blue. That was kind of silly. You could go over those in red if you want. If you're using multiple colors, I'm going to go back over those in red, because really these are points that we're plotting for our new curve. Although I did those other points in blue. Really, I just screwed up. I didn't really screw up, but I was using the red to try to make it visible, and then I did a bunch of points in blue. Anyway, the resulting curve looks like this. And maybe you're not even using any different colors anyway, so you're like, bro, keep it moving. It's pointless to talk about color changes. I'm not using different colors. There's a curve, and then sandwiched between the next two vertical asymptotes is sort of an upside down U-shaped creature. Here we go. Whoa. Not as easy as it looks. And then between the next set of asymptotes, these real extreme looking U-type curves. And there we go. Up along that asymptote, little arrows on those curves. And then you could draw half of a downward facing curve all the way to the right if you want to. There you go. So again, x values stayed the same. Just grab a point on the original curve, keep the x value the same, and plot the reciprocal y value. And finally, one where we have to do it ourselves. And what's on this last page is a summary page. This is really nice. If you're one of my students and you want to print this out and maybe tape it into your notebook, whether you're using a 3-ring binder or a spiral notebook or something. If you're using the principal notes, it's probably a 3-hole punched binder. If you're not one of my students and you don't have access to just download the PDF, I'm trying to compress this as much as I can. Can I slide it up a little bit for you? There you go. If you want to screenshot that and use this, please don't hesitate to. Otherwise, find yourself your own darn version of this thing as a full-size PDF and print it. This is a really nice resource. Domains, ranges, periods, asymptotes, a lot of good stuff on there. All right, so let's do this as quickly as we can. I am going to refer back to the graph of the original cosecant function because I don't want to make any mistakes. So I'm going to go back and look at the original cosecant graph because I want to borrow some x coordinates from here. So the upper of these two is the cosecant curve. Nice. And we've got a period that goes from 0 to 2 pi. So I'm going to use everything from here over to here. And the x coordinates that I'll use are ones that we've seen before. 0, 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. So let's use those as x coordinates. Go back down a couple of pages. And then I'm going to modify this table. I'm going to snap in these horizontal lines so we can put some original and some new x coordinates. That's a little low. X coordinates and y coordinates. And right there. And then another one. Oh. Sine x in the second row here is referring to y values. And cosecant is referring to y values. I'm just going to drop down into here. And those are going to be y values. Can I move that? No. Okay. So we have original and original. And then in red, I've been doing new and new. There we go. So what were the original x coordinates that we were working with? We just scrolled up and said 0, pi over 2, pi, 3 pi over 2. That doesn't say 3 pi over 2. Now it does. And 2 pi. I said 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. But same. And the original y coordinates, at 0, we had a vertical asymptote. So this was undefined. And then our curve came down to a y value of +1. I'm just going to snap us up there. Right, so here you can see that this curve comes down at pi/2 to a point that has a y coordinate of +1. And then we're going to asymptote and then to -1. So 1, asymptote, -1. Now this happens every once in a while. If I scroll up and down, sometimes the stuff that I've written slides out of place. I don't know why that happens. So we still have undefined here as an original y value. And then we said it goes to 1, and then undefined again, and then to -1, and then back to another asymptote. Okay. Now what are the transformations that we're going to make? Our a value here is equal to +1, so there's no vertical stretching. Our b value is equal to 2, so that's going to cause a horizontal stretch or shrink. So let's say that that modifies the period. And the period of our new function is equal to the original period divided by the b value. I got it right this time. And the original period of the cosecant function is 2 pi, and here our b value is 2, so the new period is pi. And what that tells us is that we're going to be taking our x values and multiplying them by 1/2. In other words, dividing them by 2. In other words, dividing them by b, which was a 2. Nice. What else is happening? I see that we've got a c value that's equal to, you tell me, what's the c value? Careful. Our c value is +pi/2. Because this says minus what? Minus +pi/2. So what does that do? It causes a phase shift, PS for phase shift or horizontal shift, and that is equal to c divided by b. And in this case, that's pi/2 divided by 2, which is equal to +pi/4. So we're going to be taking the graph and shifting it to the right, pi/4. How do we make that happen? We take our x values and we add pi/4 to them. We're going to multiply them by the 1/2 first. Then we're going to add the pi/4. And we need to do it in that order. And what else is happening? Hey, this one's got a d value of +1. That's going to cause a vertical shift. Vertical shift. D equals 1. So we're going up 1. And in order to make that happen, we're going to take our y values this time, and we'll add 1 to them. Nice. Let's see if we can put this into motion, graph this thing, and get out of this section. This has been very detail-oriented. All right, we're taking our original x value of 0. I'm starting here, and then I'm going to work my way across. I've got 0 times 1/2 is still 0, plus pi/4 equals pi/4. And then pi/2 times 1/2 makes pi/4, plus pi/4 makes 2 pi/4, or pi/2. Interesting, that ended up being the same. And then we move to pi. Pi times 1/2 is pi/2, plus pi/4 makes 3 pi's/4. And then 3 pi/2 times 1/2 makes 3 pi/4, plus pi/4 makes 4 pi's/4, which is equal to pi. 1 pi/4, 2 pi/4, 3 pi/4, 4 pi/4. Can you guess what the next x coordinate's going to be? 5 pi over 4 it is. Now let's modify our y values. This is much easier. All we have to do is add 1 to them. At undefined, this is a vertical asymptote. You shift a vertical asymptote up 1 unit, and what do you get? Still have a vertical asymptote. 1 goes up 1, becoming a 2. Undefined goes up, still undefined, still a vertical asymptote. Negative 1 plus 1 makes a y value of 0. This is still going to be a vertical asymptote. You can write in x comma y if you would like, pi over 4 comma tote, pi over 2 comma 2, 3 pi over 4 comma asymptote, however you want to denote it. You may fill those in. And I'm looking at my x values. I see that I'm going from pi over 4 to 5 pi over 4. I got a period of pi. Let's see, 1, 2, 3, 4, 5, that's too wide. So we're going to use 2 boxes per pi over 4. Let's go down into here. Pi over 4. 2 pi over 4 makes pi over 2. 3 pi over 4. 4 pi over 4 is pi. 5 pi over 4. Y values, vertically, what's happening? We're going as low as 0 and as high as positive 2. I can see in those red numbers right there. So I need my vertical axis to accommodate reaching a height of 2 at the very least. So I think I'm going to stick with it. I'm going to go up two boxes to 1, 2 boxes to 2. So 4 boxes up makes a height of 2. You can label up to positive 3. You can take it all the way down to negative 3 if you want. Those are the ones that I need, so I'm keeping those. And now let's wrap this up. At pi over 4, I have an asymptote. Let's make this line a little thicker. Little arrows on the ends of that asymptote, good. At pi over 2, we're at 2. At 3 pi over 4, we've got another asymptote. At pi, it says we have a y value of 0. And at 5 pi over 4, we've got another asymptote. Now, the unfortunate part about this is this doesn't give us a really great feel for what this graph should look like. I really wish there was another point here and another point here and here and here for me to draw my curve through. However, based on these 5 reference points that we've just plotted, we're going to do our best to sketch in the graph. We know that it's a confined U-shape kind of a graph that then goes up and hugs along those vertical asymptotes. It does not cave in on itself. And this one to the right does dive down, hugging, getting closer and closer to that vertical asymptote, but never touches it, never crosses it. And that is the graph of this function that maybe you would never think you'd have to graph something like that or even be able to graph something like that. And that looks really good. And then again, at the bottom is that summary page. Now I'd also like to show you quickly, and I'm going to see if I can get this to show well on the screen, but I grabbed my graphing calculator, and so I'm using a TI 84 plus, I think. And if you take this thing and you hit the mode button, which is up near the top, you go into a menu system, and if you go down, if you arrow down a couple of times, you're going to hit the spot where it says radian. So you want to make sure that that's blinking. See if we can get this to focus better. You don't need to see me. I want you to be seeing what's going on the screen right there. And it's a little touchy, and it's a little bright. Can I change that too? I'm messing up all the settings on my camera right now. What's that do? Well, not sure. What does that do? What about this one? What happens if I turn this? That doesn't turn. What about this one? What about if I go this way? Oh, I don't want to do that. It's messing everything up. Thought I had a variable nd on this. I guess not. I'm kind of bummed. Yeah, guess not. That's just the aperture. Anyway, scroll down a couple. Oops. Scroll down a couple to radians. Make sure you're blinking on radians. And then if you go into here and you click the y equals button, you can type in the equation. Now, unfortunately, it's tough to see. If I do that, does that help? It makes it worse. Anyway, I typed in this equation, and the way that I had to type it in, because there isn't a cosecant button on the calculator, I had to type in 1 divided by sine, and then I typed in the expression 2x minus pi over 2, close my parentheses, and then hit +1. And then I used this window button right here, and when you go into here, it dictates or allows you to modify the size of the window when you do your graphing. So if you don't have experience with this, I recommend that you try this, check it out, and I will tell you that I set my x-min equal to, I'm moving my cursor, you can't see my cursor. I set it to positive pi over 4. I set my x max to positive 5 pi over 4. And there is a pi button in the left-hand column. You have to use the second button, which is in the top left corner of your keyboard. You can hit second and then come over here and hit pi and type in very precisely pi over 4 and 5 pi over 4 as your x min and x max. The x scale is 1. The y min, I put it as -5, and the y max I put as +5. And if you do all of those things, and then in the top right, if you hit the graph button, you will hopefully be very excited to find out that, I'm so bummed that you can't actually see this on mine. I'm so proud. Anyway, it looks exactly like what we just graphed. So try that out if you happen to have a graphing calculator. If you don't, you could go into Desmos and graph it in there. I think I'm in focus now. And that's it. God bless you for hanging with me for this whole thing. A little over an hour, so a little over a half hour for you if you're at double speed. Keep hanging with these. Keep taking great notes. Keep being precise. And keep being patient with yourself. I know the homework assignments for these can be challenging, but it is worth it, I promise. And I'll see you real soon. Thanks again.